Okay. There we go. There we go. Okay, I am this guy, and I'm from there, and what we want to know is this Kubernetes cluster secure? We can't know if things are secure without having a full picture of all the information. This fish thinks things are good, but the dam is on the way to collapsing, and in fact, he didn't have full visibility. So we need to lock down access to Kubernetes APIs and databases and data stores, so even a compromised system does not give up its secrets easily. So this gives us more time to detect an attack. To digress on security, a point-in-time pen test has limited value, and if subsequent changes to the infrastructure cannot be easily reasoned about, managed, or audited by engineers, then a pen test is nothing more than a bureaucratic rubber stamp. Continuous security techniques constantly verify the state of a system. This gives us continued confidence in the state of our infrastructure and its security. So this talk is relatively deep. If you don't know Kubernetes security well, you will do after this. Is it safe to run multi-tenanted workloads in a public cloud? And how can we make sure that what is safe today remains safe tomorrow? So this talk is about common pawns of Kubernetes, how to harden the control plane. We'll look at what workloads and networks are and how they interact, some detail on hard and soft multi-tenancy, and finally a recap on continuous security. So the history of Kubernetes is insecure by default. Security fails to keep up with the pace of feature delivery, as with most other software packages, but this is the right decision. We know because Kubernetes is now the second biggest project on GitHub behind the Linux kernel itself. However, it had an open port available on the kubelet, which allowed us to inspect exactly what was running and its environment for a very long time. This just wasn't addressed. A lack of RBAC is another older class of exploit. This was when access-based or attribute-based access control was implemented up until 1.6. Before that point, we had a default service account mounted into every pod, and that service account had cluster admin access, meaning a remote code execution into a service running on Kubernetes was root of the whole cluster. That has now been fixed with RBAC. However, if RBAC is incorrectly configured, this is still a potential problem. SecComp was not introduced to Kubernetes until, again, around 1.5, 1.6. This is despite it being enabled in Docker and a default profile running against all images from the Docker Hub are pulled and run successfully with a default profile. Kubernetes just turns that off, as it does with user namespaces. And there's another great talk here. He went through all the vendor-supplied distributions of Kubernetes and broke them all, responsibly disclosed, and after they were patched, he delivered this fabulous talk. So, like everything in security, this is just about staying up to date. Helm, of course, didn't have any TLS or SSL between its components. This only landed in version 2.3. Helm as a templating tool is awesome. Helm as an in-cluster deployment tool, less so. And the big kahuna, the Tesla dashboard hack. This was Monero mining, and Tesla actually took the pains to forward the socket of an internal service out to somewhere publicly accessible. The version of the dashboard running at the time was able to spin up pods and again ran delegating on behalf of the API server. So from this perspective, you can do many things, but you can run a privileged pod that calls back out to an endpoint that you control. You have a reverse shell, and you can root the cluster. And of course, a mount breakout via symlink. The container storage interface, like many things in Kubernetes, things start off in tree, and then an abstraction is placed, so for example, the container network interface, and then everybody conforms to the interface as defined, and it works quite well because it allows people to prototype in tree and then extract the interface. The container storage interface is the newest of these, and a likely place for bugs, and therefore exploitation. This one in particular was a failed a failure to check the resolution of symlinks. So one could mount a volume, create a symlink to etc password or any other arbitrary file, then reload the same volume, and Kubernetes would resolve that symlink on the host. Just an example of how easy it is to add bugs, and of course all security flaws are just bugs. Again, this is fixed. We should just be up to date and not be running one of these vulnerable versions. So, minimum viable cluster security. TLS, essentially. I think I've jumped ahead a slide. But essentially, continuous security, defining everything as code, running it repeatedly, and using that code as a basis for your internal security reviews. Bringing in the security team, it kind of sounds like DevSecOps, but of course, that's just another word for correct engineering. We should just be doing these things by default. So, this is a continuous delivery slide, continuous security. It is mesmerizing and carries on for a long, long time. Right, so, hardening the control plane. This is what the Kubernetes control plane looks like. This is a diagram by Lucas Kallstrom, who's the maintainer of kubeadm and various other things. Essentially, these are the network interconnects between different parts of the Kubernetes system. TLS everywhere is the basic mandatory requirement for a Kubernetes cluster. That's because there's plenty of places to intercept traffic. Networking is complicated with many abstractions, and without using TLS, you can sniff any traffic from inside the cluster. And this is all about hardening against the potential attack or pivot. So, bootstrapping TLS, there's a lot of detailing in Kelsey Hightower's Kubernetes the hard way. The TLS bootstrap feature here is really nice. So what this means is that you don't have to encode private keys into golden base images. If we want to auto-scale a cluster, then the compromise we make is an auto-accept of a certificate signing request from a new node. But what we're saying is we've got, say, a 3-node cluster. We suddenly get 1,000 requests per second, and we want to scale that up to a 20-node cluster. We bring up the same base image from our cloud provider store or our or Pixie booting or however we want to do that, and that self-identifies itself in the certificate signing request back to the API server, which we trust because it's presenting a TLS certificate with its Kubernetes local or whatever that is identifier. And then we have this. The compromise here is that we then say, okay, well, if this request is coming from inside our network, we will automatically accept the certificate signing request, generate an identity and a certificate for the kubelet, and then we can bootstrap mutual TLS and know that we've got not only encryption, but we can also use that for authentication and then authorization. RBAC, as I mentioned, you have to enable this. It's the only way to cleanly delineate and segregate responsibilities in a cluster. You can't enforce least privilege without having something to enforce the privilege. It's a little bit complicated because, like in all things, Kubernetes is designed to be abstracted for any possible permutation of configuration you could imagine. So RBAC essentially uses these, the role and the binding abstraction. It can be very difficult to actually audit this because the concept of a user doesn't really exist in Kubernetes. Intentionally, they push that off onto federated third-party authentication. This makes perfect sense when you think about it because offboarding people in organizations is an expensive and error-prone process. So by centralizing everything and offering integration methods for authentication, and that's pluggable as well, so you can back off onto OAuth or OIDC or just JOTS or whatever your organization uses. Yeah, so basically we take this concept of a user or the tags that identify a set of users in a group, we bind that to a role, and then the role has concrete permissions on API calls, so they map quite nicely to the RESTful principles. These are some various, so CoreOS Dex is great. It's a way to essentially back off that authentication step to anything. See the pluggable connectors there, and there's various other ways of doing this. If we are on GKE, then we need to disable legacy authorization. And as well, this insecure port in general, the API server assumed at one stage that it was sufficient to allow access to this insecure port only on the local host adapter. That doesn't really work if you manage to get a DNS rebinding attack, or if somebody does get access to local host as an unprivileged user, they can then escalate by interacting with the API server. So this is now the configuration that should say on all API server configurations. And this is an example. If you do have access to that read-only port, the insecure port there, then you can pull back anything from the Kubernetes API. And you can actually do so, as you see, just with a plain curl, because apart from things like the exec call, which step up to a WebSocket, most other things are just plain RESTful calls to the Kubernetes API server that will just put something in etcd and then leave it there. And then it's up to other asynchronous operations to watch the contents of etcd and perform actions based upon them. We should also not allow anonymous authentication. This is because that leaks your server versions on this, again, very simple API endpoint. So, next, etcd. As I said, etcd is the state store, and everything operates asynchronously, which is great for scalability, of course. It is a strongly consistent model, but the cluster behaves eventually consistently. But notably here, the only access required to etcd is for the API server. There should be nothing else able to reach etcd, and as such, it can be firewalled and moved outside of the network that the rest of the cluster sits on. And of course, etcd does not come with encryption at rest by default. You have to enable client certificates for authentication. There is now an experimental flag on the API server called Enable Experimental Encryption Provider, or something similar, which allows you to place symmetric keys that are used by the API server to encrypt everything before it's written into etcd, and then subsequently to reverse that process when it reads it. Without that, a compromise of the etcd nodes is also a compromise of the cluster. So, securing workloads. We know what a container is, as does this kitty. They form the basis of the Kubernetes security model. They are just kernel primitives that Linux exposed to us, then some Linux security modules, and of course discretionary access control based on our users and file system permissions as traditionally, and finally capabilities. So, a pod is the lowest addressable component in Kubernetes. It comprises of one or more containers, and here is an insecure pod configuration. It is insecure because of this privilege flag. Now, there are lots of things a pod can do to break the security model. It can run as root, it can run as privileged, it can add cap sysadmin capabilities, it can turn off seccomp, we can have no RBAC in the service account it uses, we can mount host volumes, we can share the host PID network or IPC namespaces. That is a long and painful list. I would urge you, and there's some tooling later, to enforce those sort of things not only with pod security policies, but also with static analysis of YAML. We've moved into a stage where everything is declarative configuration, and essentially we need unit tests for those things to make sure that what we started with is what we end with. Control plane have a tool, this is called kubesec, and it attempts to quantify the risk of each individual configuration flag. So this is static analysis, but it's opinionated and on a pre-trained model, if you like. So what does it do? You submit that pod manifest that we saw earlier, and it gives you something like this, a score of -30. And why? Because privileged containers allow almost completely unrestricted host access. This also comes with, not in this version it doesn't, it also comes with an admission controller and a kubectl plugin. So that means that you can specify into a certain namespace no pods of a risk score less than, let's say, 10 are permitted. A risk score of 10 involves adding security features and not disabling them. So we can also do this at a global level or a namespace level with pod security policies. As you can see here, the AppArmor and seccomp enforcements on the annotations are a way of making sure that pods that do not specify their own seccomp or AppArmor profiles have them added. Without these, you have no, you're running unconfined workloads, which is a bad thing. So yes, there's resource linting here. We can also use kubetest, which is unit tests for Kubernetes configurations from a chap who now works for Docker, Gareth Rushgrove, and yeah, very strongly recommended. So, this is a young lady deploying herself. Very brave indeed. Right, so security primitives here. Kubernetes came from Borg, which and the Omega project, and Google attempted to build Omega from Borg, taking advantage of the basis of what they had already. But they ended up rolling Omega back because they tried a load of things and they decided that Borg was kind of good enough and well tested enough, but they added some bits. Labels are one of Kubernetes' magic primitives, if you like. So labels are how things are addressed in Kubernetes, and there is an infinite permutation of label pairs that one can use. This differs because Borg had a less addressable system, if you like, and made it a lot more difficult. So what does that mean? Services use this Kubernetes security primitive, of course, in labels because they have to address something. There's not very much to say about these, but of note is that services can be used to remap ports. So what we see here is the TCP port 443 is TLS, but actually the target port, which is where the service is pointing to on the container behind it, or the collection of pods rather, is 44, wrong way around. So the service presents 443 to external consumers, but behind the scenes it's pointing at 8443 on the pods. This is important because binding to a port below 1024 is a privileged operation. We don't want our containers to have any privilege at all if possible. So by binding our TCP services to a higher address and then masquerading as TLS using the service abstraction, we have a nice way of avoiding giving excess capabilities. Service accounts, these are, again, linked in with RBAC. We create a service account, and then we give it a role binding to a role, and then it is able to perform actions against the API server on behalf of maybe a pod or an operator, or however that works. Admission controllers. Pod security policies are just an admission controller. So an admission controller is run on the API server request stream. So as you can see here, first of all, when I do kubecontrol get pods, the HTTP handler resolves that request and offloads it internally in the API server. Then we authenticate and authorize the request. At this point, we have, this is the way it used to work, in fact, we now have webhooks which we can extend these two admission control points by. That's important because in the same way that the container network interface was baked into master, baked into tree, so were these two admission controllers initially. So this means we can now extend admission control with arbitrary policy, which is great. So what happens here is, for example, maybe at the third step here, we say we run a mutating admission controller to say, if there is no service account attached to this pod, we'll give it the default service account. Now that's traditional behavior, and that can now be reversed because we don't want to hand out service privileges where we don't want to. And then so we then validate the schema to make sure we haven't messed up anything in mutation. And then finally, we validate the object. So it could be that we validate the schema and its conformance, but when we come to actually deploy to the cluster, we may have policy that says, I won't allow any image that is not tagged in with my internal registry to be deployed. Or I may take that image and send it off to Twistlock or Aqua and check if they have scanned this and if it's got a certain number of vulnerabilities. Any critical vulnerabilities we don't deploy to production. This is super nice. Ultimately, all these things that are being described in terms of pipeline security kind of make little sense if we finally do not validate these things with admission control at the cluster. Fortunately, it's now become very easy post, I think, 1.11. But there was an initial cut of the admission controller concept, which was rolled back and changed. So just make sure if you're looking this up that things are recent. There are a lot of admission controllers, and I won't go through them all. Image policy webhook is where we would hook into Twistlock. This is essentially saying we will not allow somebody to escalate privilege via the API, which is pretty nice. There are lots of these, as I said, and this one particularly is important. So this is, again, a relatively new piece of functionality that says if I am a given node and I'm using that node's service account, that service account can only request things that the API server has already given to that node. So it means that node can't enumerate secrets in all namespaces. It can't even, if we've got a segregated cluster deployment with different node pools, can't even make requests on behalf of another node pool. This is super important, and it's, again, a really nice security boundary, because otherwise, compromise of a node is compromise of a cluster. The cluster role is complicated, and the node restriction has to go in tandem. So this authorization mode node has to go in tandem with this admission controller. There's a little bit more than standard admission control, but really imperative. And pod security policy is just another admission controller, static analysis on YAML. This is the service account one that I mentioned, and yeah, so these are the validating admission webhooks as described earlier, and they have changed in implementation. This is the experimental encryption provider that I mentioned earlier. I just spoke out of turn, and just general stuff around keeping secrets isolated. Now, one thing that we really love at Control Plane is the sealed secrets. It essentially stands up an operator pod inside a cluster, and it watches the API server. When a custom resource definition of type sealed secret is written to the API server, it will read it. It's exposed its public key to the user, so we've got an asymmetric encryption. It can use its private key to decrypt, and then it writes back the plain text or consumable secret. This means that we can store secrets encrypted outside of the cluster and push them in with secure transport that's not only secured by the TLS of the API server, but also of whichever form of RSA, let's assume. Yeah, so sealed secrets is really nice, and there's various other ways of integrating these things with cloud provider backends, for example. This is a super nice feature that means we can hand out short-lived tokens. This is attempting to gloss over the mess of service accounts. It is still alpha. Feedback is welcome if people would like to get involved. And of course, we want to continuously scan our clusters for compliance. This runs at a slightly different level from security testing because we're looking at a more general configuration. Of note here is that the kubench CIS benchmarks there for 1.2 are stuck 1 year behind on Kubernetes 1.8. Aqua Security and the NTT group are currently updating those, and we are working towards building some container standards with CIS for secure container image. Right, so at this point, we are looking at what is sitting in the container image that we're looking to deploy. So this could be, for example, vulnerable web services. Maybe we're using Apache. Maybe we've got a bash version in there that allows things to be shell shock exploited, which is remote code execution, which is the foot in the door you need to begin pivoting through infrastructure. These are really mandatory for any cluster deployment that you care about, because they will stop you deploying CVEs into production, and CVEs are published. There are exploits available. Script kiddies know about them. It's a likely route to exploitation. So, moving on to networking. 6 minutes left. Look at the complexity. It's very annoying to debug. So what we can do here is we can utilize network policy, which is essentially Kubernetes native firewalling. The important distinction here, and it's applied here. Yeah, so the important distinction here, I'm jumping ahead of myself. So this is a network policy called default deny. That actually is a wildcard. So this is a failed closed by default. I think that should just be rejected, to be honest with you. I don't like this configuration syntax, but there we go. And so here we go. Here's a network policy. And importantly, you see pod selector match labels app foo. Again, we're using the label construct to address services, but these are never validated. There is no consistency check for labels. It's one of the most common causes of operator problems and downtime, because there's no way of saying Kubernetes validate my labels. Now there can be, and if anybody ever wants to build this, do feel free. But labels are a security and operational primitive that are not enforced. It's like having no consistency on a foreign key, or no relational integrity, rather. Network policy only operates on labels and IP ranges. It does not work on DNS. If you want to block on a DNS basis, then Istio and, Istio will do this for you on its egress filter, but ultimately, DNS lookups are non-deterministic. They could be geographically load balanced, they could be round-robined, So they took a conscious decision to not permit that. That is not permitted. Service mesh. I love service meshes. Istio is kind of approaching production readiness. Version 1.0 should technically be production ready. But as with Kubernetes, the APIs are versioned independently, and the core code is what is actually 1.0. So a service mesh broadly is a way for running an overlay network as the only communication mechanism between pods. And the way we do that in Istio is with Envoy, which is a project from Lyft. That operates as a network proxy. And importantly, that pod boundary there that we see is IP tabled. So any in or outbound requests, either in, go straight to Envoy, and the downstream service, which is our containers in the pods, if they make any outbound request, that is grabbed by IP tables and rerouted to Envoy. That fundamentally is how the service mesh is enforced, and then we see that all communication then goes across the mesh. There's mutual TLS, there's enforcement, there's rate limiting, there's policy, there's all sorts of magic in there. It's really great for high compliance environments because running your own public key infrastructure is a horrible, horrible mess. Probably not that relevant for a small artisanal boutique development firm, and that tends to be the argument right now. Feature lists, yes, old stuff. All right, so it's another control plane tool. This is essentially network testing. So this is wrapping Nmap, going into the same network namespace as the service under test, and firing off, I was going to say TCP or UDP requests to identify the topology and identify white and black listing. This operates not only in Kubernetes, but it also works natively, just SSHing onto boxes in a kind of Ansible-esque way. This is a lifesaver when attempting to maintain or update policy, either security groups and NACLs, or the Kubernetes native, or Istio. Of course, it's highly recommended, but I would say that. Here is the tap output, so it fits into CI workflows, etc. Some more stuff there. Right, recap, 3 minutes. Multi-tenancy, it's great to use these minimal attack surface base OSs. Yeah, this all speaks for itself. You don't want any network routes to any of these things. Yeah, ultimately. And also, metadata APIs for cloud providers. If you can access the contents of a metadata API and the user data for the instance that your pod is running on, you can probably route that as well. So you have to proxy those things so the outbound requests to those are not accessible. And you can either do that with a dedicated IAM proxy, if you do need IAM role delegation for pods, or just block it entirely with network policy. But this is more common than one would hope. And soft multi-tenancy, we are missing a cat picture there, but I assure you it's delightful. So we isolate by namespace, limit ranges to avoid namespaces, essentially denial of servicing the node that they're on. Separate dev and test from production. Kubernetes is supposed to promise aggressive multi-tenancy, Google infrastructure for everybody else. It's not there yet. I doubt it'll be there in the intermediate future. Things like gvisor, which is Google's re-implementation of the Linux syscall surface in Golang, are what they use to prevent container breakouts, etc. There are 0 days. There are always 0 days in the kernel. When Dirty Cow came out, that was root of the cluster from inside a pod. Separate dev and test from production. Of course, image scanning, policy, all these things, everything is code. Harder multi-tenancy, co-tenant along existing security boundaries. It's kind of self-evident, but if you have data concerns or concerns about intercommunication between nodes, use traditional network tools, use VLANs if you want, use physical segregation. Kubernetes is not a panacea. You can't just multi-tenant in Kubernetes without serious consideration. And separate node pools for different tenants on a hard multi-tenancy system. There are loads of container runtimes coming. 56 seconds, I'll tell you about the interesting ones. Kata containers is Intel's clear containers running inside QEMU. And basically, that will bring up a hypervisor, start clear Linux, configure a set of namespaces inside it, and then break out of the VM for communications routes for networking back to the host. Super cool, prevents a lot of breakout attacks, Unfortunately, it's not fully, talk to me afterwards if you're interested in that. Yes, more, running kubedns will also leak across boundaries. Again, we can talk about that later. Great advice from Red Hat Dan, who is the guy who invented SE Linux, or the SE Linux guy. Use intrusion detection. Excellent. These guys all do kind of the same thing with different nuances. My time is up. Use RBAC. This is also really very relevant. And I think with small cats.
But you can talk. Well, you don't have to. Yeah. Have your time.
Okay. Well, there is. So these are just alternative ways of building Docker images without using a Docker runtime. Again, the Docker runtime runs as root. They're trying to separate this out. There's some amazing work going on by this guy, Alexis Ri, with this Umochi tool. So what he's done there, in collaboration with 3 or 4 other guys, including the Ubuntu LXC development team, they're moving towards rootless containers. That means that a container starts without privilege. A breakout of the container doesn't really matter because you're just breaking out as the unprivileged user who's running on the host system. So it's reducing that level of privilege. And he's collaborating with a dude whose name escapes me. And they've now done something called Kubernetes, which is Kubernetes with user namespaces. Now, this is why running as root inside a container is a bad thing, because the way that discretionary access control works is all based upon users. Who owns this file? What permissions does it have? And when we're running as root inside a container, that maps to the host's user identification table, which is basically etc password. That's obviously a bad thing, but nobody wants to pay the penalty of a lookup table that essentially shifts between the container's view of the user table and the host's. Now, I'm ecstatic to say that the LXC guys are working on ShiftFS, which is a file system that does that mount changing for you, and that might be ready at some point soon, incredibly. That will solve a lot of the problems here. Kubernetes disables user namespaces. Usernetes is that same group of people, so there's some super exciting stuff happening there. Right, persistent configuration, back to the cat. Again, we're just looking at putting all this stuff into pipelines. It's just run your Jenkins file aggressively, have different Jenkins for different environments, and have a production Jenkins that can run non-destructive tests against your production cluster to ensure that these things are still secure. So don't get caught out. Be proactive and preempt what's coming. The brave new world of Kubernetes has a far greater attack surface than it used to, and a lot of the problems that we see are just misconfiguration issues. So there's lots of new security primitives, but we have to test them and be sure that our configuration for their use is correct. The only way to iterate sanely and without getting woken up at 3 o'clock on a Sunday morning is with a test suite, and security testing keeps you young. 3 minutes over. Sorry I was late. Thank you very much.